This activity gives you another chance to work through the state space and transfer function representations of a system, one that we've seen in past lectures. This is a little bit different. We're trying to mix up our different examples that we see. In this case, we have two second-order differential equations, and let's see how that appears in terms of both of these different representations. Here, the input is going to be the road reference R, and the output is going to be the movement of the main body of the vehicle. So go ahead and give this a shot, and we'll go through the answers. So again, these are rather large solutions. So here I'm going to show you both of them so you can pause and take a moment to compare it with your answer to see if you got the same thing. Again, it's possible that you could have defined your variables a little bit different, where perhaps what I'm calling z, I'm calling it z simply because we already have an x here, but essentially the new state z could be defined in a different order. So let's go ahead and go through both of these representations. When we do state space, what's going to happen here is that you're essentially going to go through what we kind of have gone through before, but you're going to go through it twice, once for the x variable and once for the y variable. And so we'll see how that works out. So in this case, we need variables that represent everything that's essentially in these two differential equations. Not the very highest order terms, but all of the other terms. So we need something for x, we need something for y, we need something for x dot, and we need something for y dot. And so that's what we're defining here. I'm defining the two variables x and y as z1 and z2, and the derivatives z3 is equal to x1 dot, and z4 is equal to y dot. So now we just go through. Now, theoretically, this should be enough. So we have second order here and second order here, and the way it works is that those add together. So we need two variables for each of those equations. And so that would mean that we'd need 4 state space variables, and so that's what we've defined here. So if we were to calculate z1 dot is just x dot, and that's what we defined as z3. z2 dot is the derivative of what we defined z2 to be, which would then be y dot, and that's exactly what we defined z4 to be. So now, what's interesting now is the fact that now we get two equations that kind of have quote-unquote interesting behavior, and that's because we have two second-order differential equations, and that's fundamentally different than having one fourth-order differential equation, which is what we had in our first example in this class. So z3 dot is x double dot. And where does that appear? It doesn't appear up here in our definition of our state space variables, so we have to come back to our original differential equations, and x double dot appears here. And so we're going to use that and solve for that variable in terms of everything else. And the important thing and the beauty of state space is the fact that we've already defined variables for all of these other terms. And in this case, R is something that is our input. So we just write that out just like that, and that's exactly what that's exactly the definition based on the differential equation. Similarly, for z4 dot, we're going to define that becomes what z4 is, take the derivative of that, that's y double dot, and now we come up to this equation and grab y double dot in terms of everything else. So when we move everything to the other side, we find the terms that correspond to z3, z4, z1, and z2, and that allows us to now write all of our new variables, the derivatives of all of our new variables, in terms of all of our new variables. I'll let you go ahead and put that into state space form, and let's go ahead and move on to then the transfer function approach, where we are now just taking the Laplace transform. Now we have two equations, and we'll take the Laplace transform of both. We have second order derivatives, so we're going to get s squareds. We're going to also get linear terms, essentially s multiplying the terms when we have these first order derivatives. Again, we're not interested in our initial conditions right now because we're just specifying that transfer function. And so that's going to ultimately get us down to a coupled pair of equations that have both x's and y's in it here. And so now we have two equations and in this case two unknowns, and so we can get rid of x because what we're really interested in is what is the relationship between the output, which is y, and the input, which is r. One of the ways that you can do that instead of solving for x here and then plugging in is simply just to use this equation to produce x in terms of y. And then that is something that could get plugged in here. And that simplifies a little bit of the algebra. And that's how we get back to the solution for the transfer function.